Heap memory allows us to create memory that's completely independent of the lifecycle of the function, unlike stack memory. Let's see how this works out. In C++, if we ever need memory that's longer than the lifecycle of the function, we have to use heap memory. The only way to create heap memory in C++ is the use of the new keyword. The new keyword is an operator in C++ that's going to return a pointer to the memory address starting of the new data, and not an instance of the data itself. What that means is a new C++ operator is going to do three things, and it will always do these three things. The first thing is it's going to allocate memory on the heap for a data structure, whatever the data structure is that we're allocating. It's going to initialize that data structure, and it's going to return a pointer to the start of that data structure. We use the term data structure here because we're going to build more and more complicated things beyond just a cube as this class progresses. But for right now, we can think of this as just a simple integer, as a double, as our cube, or anything else. And the only time this memory is ever reclaimed is when we use the delete keyword. So it doesn't matter if we return from the function, doesn't matter if the function ends. The only time the system ever gets back this memory is when we use the delete keyword. So this memory is extremely powerful, but also has an extremely long life cycle if we don't take care to release this memory. So looking at the example of a piece of code, we see that this code is going to actually allocate two different variables. The first variable is int star num pointer. So this int star means it's an integer pointer, and its name is num pointer. And this is going to be on the stack. So notice, this is just an ordinary variable. There's nothing special about it. Because it doesn't involve the new keyword, num pointer is on the stack. Its value is going to be a new integer. So new int means that we're going to create heap memory, enough heap memory to store an integer, and that integer is going to be pointed to in our stack memory. So here our stack memory points to our heap memory. The heap memory has enough memory to store an int, and that heap memory is going to exist for the entire length of our program unless we call delete. So let's actually see this code that we just went over actually run. Our main program for this lecture involves a num pointer that allocates a new integer. Then we're going to print out all of the properties of this value. So the first thing we see is num pointer on the stack is going to be a pointer that points to heap memory, and that heap memory is going to be enough to store an integer. If we see out the contents of the dereferenced num pointer, we're going to look at num pointer and follow the pointer and see what is on the heap. Right now, we haven't put any memory into the heap, so we have no idea what's in this memory. It's going to be whatever's laying around from the operating system. So it's going to print out just a mysterious value here on line 13. So the first number it prints out when we run this program is going to be any random integer. We have no idea. The second number is going to be the contents of num pointer itself. Num pointer is an integer pointer, so the contents is going to be the address of heap memory. Stack memory always starts at a high address and grow down. Heap memory starts at low addresses and grows up. So the value in num pointer is going to be a somewhat low number. So this might just be the memory address 12345. This number is going to be significantly smaller than a stack memory address. The address of num pointer is going to be a very large address, since this is an address that's on the stack. We then set the dereferenced num pointer to be 42, which means over here in the heap memory is no longer mysterious and unknown, but the heap memory now has the value of 42. So after setting the value equal to 42, num pointer is going to have the value of 42. The memory address of that value doesn't change. It's going to be exactly the same as we see up here. And the address of num pointer is also not going to change. It's going to be the exact address we saw earlier. The only thing that changes when we set the dereference value of num pointer to be 42 is the actual value stored in the dereference memory. So let's go ahead and run this program and see if our intuition and understanding of this code actually matches up with reality. So going into the CPP heap memory directory, we go ahead and run make since it's the first time we're running this code. So we can go ahead and compile this code, run /main. And here in the main, we can go through these lines and see what happens. So num pointer has a mysterious value at the beginning. It happened to be 0. On your system, it may be 0 or it may be some random large value. It just depends on what was in that memory before the program got access to that memory. The second value is num pointer, and that is a memory address, which is a rather small value. So this is what we expect. We said that num pointer points to a heap memory address. That heap memory address is going to be a small number. And then the memory address of num pointer itself is a stack memory address, and it's a large number. When we assign num pointer to 42, num pointer becomes 42. And these memory addresses stay the same. This is C87010, C87010. Awesome. And this ends in C1900. This also ends in C1900. So the address of both num pointer and the memory that num pointer is stored in is exactly the same. The contents of num pointer is the only thing that changes. So now you've just created your first set of heap memory. Let's go ahead and explore this with diagrams and understand how heap memory interacts so that we have a better understanding of how this all works. So here's a memory layout diagram of a system where we have the stack memory here on our left. And we know this is stack memory because of these extremely large values in memory. Again, the memory address on a certain system is going to be unique to that system, but we know that stack memory is always going to have large values. Heap memory, on the other hand, is always going to have small values, and heap memory is going to start at the small values and grow up, while stack memory starts at large values and grow down. So running the heap1 CPP program, we see the first thing we do is we allocate an int star p equal to a new int. So int star p is going to be allocated here on the stack, and this is going to be a type int pointer named p, and it's going to point to a value on the heap. So it's going to allocate enough room to make an integer. We don't actually have a name for this. We only have a pointer that points there. So this is the dereference value of p. Second thing is cube c. So we have another pointer, a cube star c, and that's over here on the stack. And that value points to a new cube over here on the heap. So now we have 2 stack variables and 2 heap variables. And on line 15, we say the dereference value of p is 42. So we can look at p, follow its arrow, and that value is now 42. And line 16, we say that the dereference value of c, which is a cube, is going to have its length set equal to 4. And then the very last thing we see is we finally see the use of delete operator. So here the first thing we do is we delete c. So when we delete c, we look at the variable c, we see what memory it's pointing to, and we go ahead and delete this memory, giving it back to the system. And then we delete p. And we delete the memory here as stored in the integer, and we give it back to the system. So notice that there's something still left here. We have the stack memory, and the stack memory will get deleted when main returns. But we also have these pointers that point to memory that doesn't actually contain any data for us anymore. So this is a big problem. And there's a solution to this in C++ called a null pointer. So the keyword null pointer, nullptr, which if you come from a C background in C, this was just capital NULL. C++ will use null pointer, and that points to the memory address 0. So null pointer is defined to be pointing to nowhere. It's never going to be used by the system, and it will always generate a very specific kind of error called a segmentation fault if we ever access the null pointers. And you can never delete 0. So it's an address that can't be deleted. It's an address that points to nowhere, and it's an address that's going to generate an error every time we use it. So it's a way to provide some safety so that we don't have the dangling pointers. What that means is if we go look at this slide, what we really want to do is say that C is equal to the null pointer. C is equal to the null pointer as soon as we finish deleting C. So C gets deleted, and then C points to nowhere. Next thing is P gets deleted, and then P should be equal to the null pointer. So P also points to nowhere. The other last bit to note is we've been using this crazy syntax of doing *C with parentheses around it. This allows us to do the correct order of operations, but this gets really, really clumsy, and you're never going to see this in real code. Instead, C++ has a final operator, which we call the arrow operator, that allows us to access the contents of a class when that class is being pointed to. So when the object is stored via pointer, we can access the member functions using the arrow operator. We can say for our cube, for example, C, arrow, whatever we want. This is identical to this kind of crazy syntax of saying we're going to dereference the value of C and then use the dot operator to get at get volume. Instead, we have the C with an arrow operator, which allows us to dereference C directly and get right to the member functions. So let's look at one more piece of code. Here's heap 2. In heap 2, we have cube C1, which is a new cube. So here on the stack, we allocate cube pointer C1. This points to a cube here on the heap. And then cube C2 is allocated here on the stack. And then we point this to the exact same value C1 points to. So notice we have two pointers that point to the exact same cube because C1 points to a new cube and C2 points to C1. And now we say C2's cube. We're going to do the arrow operator, which allows us to follow this arrow. It's the dereference operator, but for classes. And we're going to set the cube's length to be 10. And then we're going to go ahead and delete C2. So if we delete C2, we follow its arrow, and we go ahead and delete this data and clear it out. Then we delete C1. If we try and delete C1, our data is not there. We've just deleted something that we shouldn't delete. So because the data is not there, you're going to expect the compiler to give us an error because it's going to try and double free memory that doesn't exist. So we are not going to run these programs right now, though you have the source code. Instead, in the very next lecture, we're going to go over 4 different puzzles, and we're going to puzzle over exactly how heap memory works and run lots of examples in that one. So get ready for some awesome coding, and I'll see you in next lecture.